Hi guys, and welcome back to the second part of Hazardous Earth. Today we are going to be looking at tectonic hazards, and the first thing that we're going to do is look at the structure of the Earth. So the interior of the Earth is divided into several layers, the first one being the crust, and the crust is the uppermost layer, and this is where we live. It's a rock layer that forms the upper part of the lithosphere. And it's split into tectonic plates. And the two types of tectonic plates that we have in the lithosphere are the continental crusts or continental plates. Those ones are made of granite. And then we also have oceanic plates, which are made of basalt. These ones are underneath the ocean. Then we have the mantle, which is a second layer of the Earth. This is divided obviously into the upper mantle and the lower mantle. And the upper mantle is the asthenosphere. Now, the temperatures in this particular layer are 1300 degrees Celsius, well, around 1300 degrees Celsius. And because of that, the rock in the asthenosphere here is in a molten state. So, in other words, it has melted due to the extreme temperatures or to the high temperatures, and it's in a semi-liquid state. So it's almost like, we could compare it to porridge because it's quite thick in its texture. And so, yes, it's a molten rock. Now, the lower mantle has temperatures of between 1600 and 4000 degrees Celsius. Then the next layer of the Earth is the core, obviously, and this is the innermost part of the Earth. And the temperatures here, obviously, are a lot higher again. They range between 4000 and 5000 degrees Celsius in the outer core. And the outer core is made of iron and nickel. That is a question that you could be asked as a short question, 1 mark or 2 mark question in the examination. Then the inner core has temperatures that sometimes will go up to 5,500 degrees Celsius. And this particular layer is solid due to the pressure that is being exerted by the layers that are sitting on top of it. So why do the Earth's plates move? So the Earth's plates move due to convection currents inside the mantle. Now we have already mentioned that the mantle is the molten layer or semi-liquid rock that is just below the lithosphere, which is the crust. And this area obviously has high temperatures, like we had said earlier. And that heat within the mantle and radioactive decay causes convection currents within that molten rock or the magma. And this heat causes, or the convection currents cause the magma to rise up towards the crust. Now, just for the purpose of our knowledge, radioactive decay is the heat that is given off as elements such as uranium within the mantle become unstable and release particles from their nuclei. Okay, so if we look at this diagram here, we can see that as that heat is being transferred through the mantle and through the convection currents, the magma rises up to the surface. So it gets up to the crust here. And when it gets up to the crust, that is when we have step 2. And that is where the magma will spread out along the surface. And as it does that, obviously, some of the magma is stuck to the crust up here and is likely to drag that plate that is at the top, the lithosphere, the crust, is likely to drag it sideways. Now that there is what causes the plate movement. Now because the magma is now near the surface, it's likely to lose temperature. And due to that loss of temperature, it now becomes heavy and dense and begins to sink back towards the asthenosphere. Okay, as you can see here, these are blue arrows representing cooler magma, which now is heavier, it sinks, and then gets back to the asthenosphere and then is warmed again and then brought back to the surface, and that process repeats itself. So over time, the plate that is up here in the lithosphere here is going to be dragged apart very slowly, okay, on both sides here. And that is what leads to plate movement on the crust. And the other thing I'd like to mention here are hotspots. So the parts of the Earth where the heat moves to the surface are called plumes, right? So like here, this particular bit here, this is a plume here because magma is coming up towards the surface or towards the crust. And these bring lava obviously to the surface and form volcanoes where the lava breaks through the crust. And if these plumes are in the middle of a tectonic plate, they form what are called hotspots. Now, with hotspots, they are normally in one part of the Earth, and that means that as the plate, if they're in the middle of the plate and the plate is moving, it means that the plate will keep moving over that particular plume, and over time, because the plate is moving, you will have a series of islands that are likely to be formed by the magma that has reached the surface. An example of that happening is Hawaii, where you have a series of islands on that particular plate. So the next thing we'll talk about are the Earth's tectonic plates. So we have a map here that shows those plates. And as we can see, there are two types of plates. We have the plates that occur over land or that form on land, like the African plate here, the Eurasian plate, the North American plate, and the South American plate. So these continental plates are 30 to 50 meters thick and are made from granite, which is a low density rock. And these ones are a lot lighter. These are continental plates are compared to the oceanic crust. The oceanic crust obviously is forming under the oceans. So examples here would include the Pacific plate that you can see here. You have the Nazca plate and so on. Pacific plate, Nazca plate and so on. And these are a lot denser than the continental plates and are 6 to 8 meters thick. Now, as we said before, these plates are on the lithosphere, obviously, and are being moved by convection currents within the mantle. So they are moving in different directions. And as you can see here, there are arrows that are showing the different directions in which the different plates are moving. So the Nazca plate, for example, is moving towards the South American plate. And then here the Pacific plate seems to be moving away from the Nazca plate. So that is what leads to or determines the different types of plate boundary that we are going to be talking about briefly. So those types of plate boundaries are convergent plate boundaries, and convergent plate boundaries are where two plates are moving towards each other. So an example of that is the Nazca plate here that is moving towards the South American plate. As you can see here, the South American plate is moving this way and the Nazca plate is moving towards it here. Then we also have divergent plate boundaries, which is where plates are moving away from each other. So an example of that is the Pacific plate here and the Nazca plate. So those are moving away from each other, and that is forming a constructive plate margin that we shall talk about a little later on. Then we also have conservative plate boundaries, and at conservative plate boundaries, the plates are trying to slide past each other. So from the different types of plate movement that we have just talked about, we get four types of plate boundaries or plate margins. And the first one we'll be talking about is a destructive plate margin. So here, as we can see, we have two plates and one of them is continental. So this plate here is a continental plate. And this here is an oceanic plate. You can see that the ocean is just above it. And they are at a convergent plate boundary. So they are moving towards each other. And as they do that, because the oceanic plate is a lot heavier and denser than the continental plate, like we had mentioned before, that oceanic plate is going to subduct or, sort of sink below the continental plate, and as it goes underneath it, and as it does that, it's likely to cause, well, the friction that it's going to cause is likely to lead to earthquakes. And also because it's sinking towards the asthenosphere, so the upper mantle, where the temperatures are fairly high. We said that the temperatures in the upper mantle are around 1,300 degrees Celsius, meaning that that plate is going to begin to melt. And as it melts, it's going to add a lot more magma or molten rock in the mantle, and that is likely to lead to the mantle having a lot more pressure. Now that pressure could be released eventually in the volcanic eruption here. And the type of eruption that is likely to take place here is one that is very, very explosive, because the magma that we get in these types of plate boundary is normally very high in silica content, and therefore is very thick and viscous, and also very, very explosive. And because it's thick and viscous, the lava that comes up to the surface, well, once the magma is on the surface and is now lava, the lava is not going to flow over very long distances because of its thickness. And that will lead to what are referred to as composite volcanoes, which are quite steep. So this here, for example, is a composite volcano. So the second type of plate margin is a collision plate margin, and this also is happens at a convergent plate boundary, where two plates are moving towards each other. But in this case, it's not a continental and oceanic crust or plate that are moving towards each other. Instead, there are two continental plates that are moving towards each other. Now, because they are both the same density or a similar density and weight, they are going to push towards each other, and the land in between them is going to push upwards. So that buckling upwards and pushing up is going to form fold mountains. An example of fold mountains that have been formed in this way are the Himalayas. And at these plate boundaries, we get earthquakes, and then obviously fold mountains as well. So the third type of plate margin is a constructive plate margin. So these also happen these happen at a divergent plate boundary. And in this case, as you can see here, there are two plates, they are moving away from each other. So it's a divergent plate boundary. Now, as they move away from each other, they normally will create some space or a gap in between them. And as a result of that, magma will well up from the interior of the earth or from the mantle and find its way to the surface. Now, when that happens, it normally will form a shield volcano. And the reason for that is because the lava that is coming from below the surface is basaltic lava, right? Which is likely to be thin and runny. And because it's thin and runny, it's going to flow over longer distances. And due to that, it's going to form a gently sloping volcano. And that is why we call them shield volcanoes, because they are not as steep-sided as the composite volcanoes that we saw at a destructive plate boundary. So at a constructive plate boundary, we will normally have shield volcanoes, and we will also get earthquakes because of that earth movement or plate movement. So the fourth type of plate margin is the conservative plate margin, and this happens at a conservative plate boundary, which is where you have two plates that are sliding past each other. So trying to slide past each other. So they could either be trying to slide past each other in different directions, or sometimes they could be moving in a similar direction but at different speeds. Now, as they try to slide past each other, sometimes they are likely to get stuck. And because they are still trying to push past each other, pressure is likely to build up. Now, that pressure will be released suddenly at the focus of the earthquake below the ground, which is where the rock would give way. And as a result of that sudden release of that pressure that had been building up, seismic waves are going to be transmitted towards the surface, where they will reach the epicenter, which will be right directly above the focus on the ground, and those vibrations caused by the seismic waves are then going to impact on the surrounding area on the lithosphere. So at conservative plate margins, we will get those earthquakes. So the first case study that we are going to do of volcanic eruptions is an LIC case study. So one that took place in a low-income country. Now the country we are talking about here is the Democratic Republic of Congo, and the volcano is Mount Nyiragongo. So the information has been summarized here, and I'd like us to go through it. And the first thing that we are going to discuss is why countries such as the DRC are more vulnerable and at risk from volcanic eruptions. Well, they are more vulnerable than other countries. So the area around a volcano will usually be fertile because when the volcanoes erupt, they will normally deposit new rock into the area, and the magma normally, well, the lava after it has it has cooled down and turned into soil, normally is very rich in nutrients, and therefore people can grow food. So as a result, a lot of people in poorer countries will live near volcanoes even knowing the dangers, because they don't really have a choice as to places they can live, because they are quite poor. Okay, and then the second reason why they are vulnerable is because their houses are not made from very sturdy material, meaning that they will collapse, for example, when there's an earthquake that has been caused by a volcanic eruption, because we do know that volcanic eruptions are actually accompanied by earthquakes as well. Then the next reason why they are vulnerable is because their communication systems are poor. And as a result, people may not be able to evacuate on time. Now, that will obviously lead to a lot more deaths and injuries from the volcanic eruption. Then the next thing is that recovery will take a long time, because a lot of these people are not going to have any savings or insurance, and then the relief efforts are likely to be reliant on international aid, because the countries are quite poor. So what happened at Mount Nyiragongo, and why did it happen? So Mount Nyiragongo lies on a divergent plate boundary where the Nubian plate is moving away from the Somalian plate. So this allowed a river of lava to pour out of the volcano, covering a 1,000-kilometer wide radius. And this greatly impacted the city of Goma, which is 20 kilometers from the volcano. So what were the impacts then? So as far as the social impacts are concerned, there were 147 deaths, 400,000 people were evacuated, 125,000 homes were destroyed, medical centers as well were damaged, and mains water supplies were also affected, leading to threat of disease, because obviously if mains water supplies have been affected, it means that people are not likely to have access to clean water, and that can lead to diseases such as cholera and typhoid. Then economic impacts. 1/3 of Goma, which is a fairly sizable city in this area, was actually destroyed. So the lava also covered the runway of Goma Airport. And that was a problem, obviously, because bringing in relief or aid from other countries was a problem, and then trade was also a problem. It impacted tourism and so on. Then we have poisonous gases that caused acid rain and affected farming and people's livelihood. Then there was also widespread looting, meaning that businesses lost money because people were going to shops and just looting them. And then the poverty also meant that people could not rebuild their homes. So like we had mentioned earlier, a lot of these people will not have insurance, and therefore will find it difficult to recover. Then as far as environmental impacts go, Lake Kivu was poisoned by the sulfur dioxide coming from the lava. And there was also acid rain as a result of the sulfur dioxide as well. Now that obviously impacted on the ecosystems that are in this particular lake and around the area. So what about the relief efforts then? Now, because the DRC is very poor, most of the relief and aid was led by the UN and Oxfam. So it was led by international organizations. So the UN, for example, sent food, and then governments around the world as well gave money for the refugees. So these are people who had to move away from the area around Mount Nyiragongo, and some of them actually went as far as Rwanda, and therefore were refugees in Rwanda, and therefore they needed financial assistance. So governments around the world gave $35 million dollars to help these people. Then the World Health Organization provided emergency measles vaccinations. And these here obviously must have been due to the hospitals in the DRC being damaged by the volcano, and therefore not having the vaccinations are in stock, and therefore needing somebody else to bring those vaccinations to them. Okay. So our HIC case study is Mount Sakurajima in Japan. And again, we have a summary here of what happened there. We're just going to go through it very quickly. And we are going to start off with a background and what happens at Mount Sakurajima and why. So it's one of the volcanoes located on a convergent plate boundary where the Pacific plate subducts beneath the Eurasian plate. As we said, when we have subduction taking place or a destructive plate boundary like there is in this case, the volcanic eruptions are normally quite intense and quite explosive. So it's an active composite volcano that sometimes erupts over 200 times a year. Now that is quite frequent. That obviously will beg the question why people continue to live there, but we'll go on to that a little later on. So the eruption causes hazards such as poisonous gases that bring acid rain and that destroy vegetation. And then the ash and lava can also destroy buildings and farmland. Then you also have volcanic bombs that are thrown up from the volcano, and you have pyroclastic flows obviously as well, which flow down the volcano, and those are a major hazard. So why do people continue to live there then? So this particular area is good for tourism, and people get income from tourism and therefore just continue to live there. So there are hot springs due to the geothermal energy that is coming from within the earth in this particular area, and those hot springs obviously are a tourist attraction, and people also come to see the lava flows now that the volcano is fairly active. Then we also have the fact that the soil here again is fertile and is used to grow rice and tea. Then next, the lava flow joined the volcano to the mainland. So initially, the volcano was, was not, there was water in between the volcano and the mainland, but the lava flow over time has joined that volcano to the mainland, and that happened in 1914. So that made it a lot more accessible, and therefore more people can now access it and actually live around and about it. Then lastly, there are a lot of jobs available in fishing, and there's also a port and urban areas around the bay. So in terms of economic activity, it's quite a vibrant area where people can actually come and work and live and thrive as a result. So Japan, as we know, is a HIC. So how do they monitor the volcano and prepare for an eruption then? And the two main effects that they are wanting to prepare for are the primary effects. And primary effects happen directly due to the volcanic eruption. And these will include earthquakes, lava flows, and volcanic gases. Then we have secondary effects, and these happen in the days and weeks after the eruption. So examples would be like water shortages and diseases as a result of the primary effects. And so how does the Japanese government monitor the volcano and prepare for the eruption? So they have constructed several things to try and help them deal with any volcanic eruptions that may occur. And one of the things that they have done is that they have constructed concrete shelters. Now, those shelters are obviously places where people can take refuge in when the volcano is active and when it's erupting, so that they can, shelter away from the lava and any other, danger like volcanic bombs and so on, pyroclastic flows and so on. Then they also have concrete diversion channels. Now, these are obviously to divert the lava away from the areas that are of value. So, for example, if we are talking about, either tourist resorts or people's homes, if you have those concrete channels, diversion channels, then they will direct the lava away from those areas that are of value and which have got humans in them. Then they will also use seismometers. Those seismometers will give an idea or indication of how much, of earthquake activity within the volcano, because we know that if earthquake activity in the volcano increases, it means that that volcano is likely also to erupt, and therefore they will use those seismometers to monitor the volcano all the time. They will also monitor the hot springs, and those hot springs are being monitored because any increase in the temperature of the water in those hot springs could indicate that the volcano is likely to erupt. Then we have also tilt meters, and tilt meters are used to monitor any bulges that may begin to develop on the flanks of the volcano. So if the tilt meter indicates that there is a bulge that is developing, then it means that there is lava buildup just below the ground, and that would indicate that that volcano is likely to erupt at any time. So that then would give people the opportunity to evacuate the area so that they are not in danger of the hazards that would be caused by an eruption. Then the other thing that they do as well is they use helicopters to monitor how much ash is coming out of the volcano, how much steam and so on is coming out of the volcano. And if there is an increase in that again, there's a likelihood that that volcano could erupt at any time. Okay. Okay, moving on to earthquake case studies. And the first one is an LIC, and that is the Nepal earthquake. Actually, there were two earthquakes that happened in Nepal, and those earthquakes took place in April and May of 2015. So Nepal sits on a collision plate boundary. So we said that this is where two plates are converging, and both of them are continental plates. And the plates we are talking about here are the Indian and the Eurasian plate. And the other thing we'll look at is why Nepal is vulnerable. So Nepal is one of Asia's poorest countries. It's also quite rural and isolated. That means that if you would like to send information or warnings, for example, about a pending earthquake, then people might not get the warnings, might not receive the warnings, and therefore will be quite vulnerable. Then in terms of accessibility, that could be a problem as well, because it's difficult to get to reach those areas in case there is an earthquake. So relief efforts would be hindered by that accessibility or poor accessibility. Okay, so on the 25th of April and 12th of May, it was hit by two earthquakes of magnitude 8.1 and 7.3 on the Richter scale. And there were 400 aftershocks following these two earthquakes. So what were the impacts? So the social impacts here, so there were 9,000 deaths, 23,000 injuries, and over 800,000 homes were destroyed. So 3 million people were homeless, and drinking water supplies were, disrupted, and drainage systems also destroyed, meaning that sanitation was poor, and this obviously led to health risks. Now, as far as the economic impacts are concerned, $7 billion worth of damage was done by the earthquake, and that is quite a a substantial amount of money, especially for one of Asia's poorest countries, because that $7 billion was equivalent to a third of Nepal's GDP. Uh, Also, on top of that, the tourism industry was affected, which also brings GDP or money into the country. And the relief efforts were affected by the closure of Kathmandu Airport, which is also a problem because in terms of trade through the airport, that also was disrupted. In terms of tourism, that was disrupted. So the earthquakes actually caused quite a bit of disruption here. Then the farming industry as well was disrupted because the crops were destroyed, and people were also not able to farm, and so on. So what were the international responses then? So we know that we've just talked about the fact that Nepal is quite poor, which means that their government would not be able to respond as effectively on their own, and therefore they had to greatly rely on international relief efforts. So the UN, for example, provided tents, blankets, water, and hygiene kits for people that had, were victims of this earthquake. And then there were search and rescue helicopters from the USA and China. Now, as we said, that Nepal is surrounded by the Himalayas, and therefore some of the places are quite inaccessible. And obviously, Nepal does not have, their own helicopters, emergency, helicopters that would go and rescue people. So they had to rely on the US and China. Then military troops were sent by India to help search for people in collapsed buildings and also to clear the rubble. Then other countries also gave donations to try and help during this difficult time for the Nepalese people. And the Indian government, for example, pledged $1 billion. The Chinese government committed $500 million, and so on. You can have a look at the information there. So the last case study that we're going to look at is a HIC case study, and that is of the Japan earthquake and tsunami of March 2011. So again, we have a summary of information here regarding that particular earthquake and tsunami, and we'll go through it very quickly. So the background here, information that we have is that the magnitude of the earthquake was 9.1 on the Richter scale. And the earthquake hit the region of Sendai on March the 11th, 2011. Now, that earthquake also triggered a very huge tsunami. So the cause of the earthquake was subduction of the Pacific plate under a portion of the Eurasian plate. And the duration of the earthquake was 6 minutes. So the shaking lasted for 6 minutes, which is a substantial length of time for an earthquake. And the focus was 30 kilometers deep, and the epicenter was 70 kilometers from the Sendai Bay coast. Now that means that where the shaking started was 70 kilometers from the coast, giving this particular earthquake an opportunity to create a massive tsunami that started 70 kilometers away. And we know that the tsunami will ordinarily become larger as it reaches the coast, especially if it has traveled over a longer distance. And the tsunami wave height, obviously, as a result, was almost 40 meters, which is quite a huge wall of water. Okay, so what were the primary effects then? So the total economic cost was $235 billion, and that made it the costliest natural disaster in world history. And there was serious damage to buildings, roads, bridges, railways, and infrastructure. So the number of buildings that was destroyed was over 300,000, and over 2,000 roads obviously were also destroyed. So as far as the secondary effects go, there were over 18,000 deaths. Now, these included several thousand victims who were actually never recovered, and then there were 26,152 injuries. So there was also a problem at the nuclear power plants at Fukushima. So there was a meltdown of 3 of the reactors, and this was as a result of flooding of the cooling systems. So the tsunami water actually went into the cooling systems and disrupted it, leading to radiation release and evacuation zones. Now we know that obviously if you have a nuclear power plant, it's likely to release very harmful radiation, and that is why people were evacuated from the area. So it took a long time to clear the debris and to rebuild, and that disrupted businesses and schools, due to the time that it took for this cleanup process to take place. People were left homeless and unemployed for a long period of time as well. So Japan, obviously, again, we know is a wealthy country, and therefore, how do they prepare, or how are they preparing for future earthquakes since that time? So they have earthquake drills in place, and people also have emergency kits. And as we know, in Japan, they normally will construct earthquake-proof buildings. Now, those obviously tend to sway with the movement of an earthquake, and therefore are unlikely to collapse. Then they also have automatic gas supply cutoff. Now that means that when they sense an earthquake, the gas supply is going to be cut off such that any fires that may be a result of the earthquake are avoided. Then they also have a system where their trains will detect an earthquake within 2 seconds and will also automatically shut down or stop. Now that obviously is a good thing because it avoids the problem of derailing of trains during an earthquake. They have also built tsunami walls to ensure that they have some kind of protection from any water that may be coming in via tsunami from the ocean. Okay, so that brings us to the end of this particular video. I hope you enjoyed it and you have learned from it. And again, good luck in your examination on Wednesday. Okay, bye-bye.